Exploring group isomorphisms graphically. In this video, we'll go over some key concepts and then prove the following conjecture about group and graph theory, that isomorphic groups will have at least one pair of isomorphic Cayley graphs. And then we'll go over some implications. If you aren't familiar with set theory, linear algebra, and modular arithmetic, you should pause this video and view some of the resources linked here. And just as some motivation, graphs, groups, and isomorphisms are key areas in mathematics, and understanding these connections and their shared properties will aid first-year math students in their future studies. Let's dive right into algebraic groups. A group is a set with a binary operation which is closed and has the following three conditions. That operation is associative, it has an identity, and every element has an inverse. One example is the integers with addition. Some helpful properties of groups include that there is only one identity element in a group and that each element will have exactly one unique inverse. We also have cancellation. If AB equals AC, then B equals C. Another key aspect of groups are generators. A subset of the group where every element in the whole group can be expressed as a combination of elements in that subset is called a generating set. And an example here is the integers with addition. One is a canonical generating set of any integer because we can write any integer as a sum of ones and negative ones. There's another example here that's 3 and 5 because we can use those to create a 1. In general, generating sets are not going to be unique, and there will be many for any given group. In mathematics, an elementary graph is a combination of two sets, a vertex set and an edge set, as we can see to the right. If pairs of vertices are unordered, the graph is undirected, and if they're ordered, we call the graph directed, and we denote that with arrows instead of lines connecting nodes. A graph does not care at all about the location or layout of the nodes, just the sets and the connections between the elements. We can modify graphs by labeling, coloring, or weighting their edges, and the degree of a vertex is the number of edges which are incident to it. Additionally, in mathematics, an isomorphism is a map between two objects which preserves structure. In linear algebra, we have isomorphisms between vector spaces, which are specified by invertible matrices. In abstract algebra, there are group and ring isomorphisms. In graph theory, we have graph isomorphisms, and topology also has isomorphisms. To review, a bijection is a one-to-one and onto mapping between two sets. And an isomorphism is a bijection which also preserves the structural operations of that object. Isomorphisms are a type of equivalence relation, which tells us that two items which are isomorphic are very similar and are akin to equal or equivalent. Regarding groups, a group isomorphism is a function from one group to another which is bijective and preserves the group operation. We see here that the multiplication on the left-hand side is within the first group, and that translates directly to multiplication between objects on the right in the second group. One such example is from the real numbers under addition to the positive reals under multiplication, and that map's given by e to the x. Some important properties of group isomorphisms include that a generator in one group must map to another generator in the other group, and that the identity must map to the other identity. We can see here an illustration of how phi, our bijection, maps elements from one group to the other. In terms of graphs, graph isomorphisms are a bijection between the vertex sets which preserve edge structure. Two vertices will be adjacent in G if and only if their images are adjacent in H. This preserves a ton of properties, like the number of vertices and edges, cycle lengths, degrees, connectivity, and more. We can see here that we have a bijection between the letters A through E and the numbers 1 through 5. And when we go here to the graph, we can see that there's an edge between A and B, so there's an edge between 1 and 2. And this is exactly what we've just described. When we want to represent a mathematical group as a graph, we use a Cayley graph. And a Cayley graph is just a graph that encodes the structure of a group. These depend heavily on our generating sets, which we assign each element of a color. and those will correspond to the edges in our graph. We will also create one vertex in the graph for every element of the group. There's a key property here that Cayley graphs will have an equal number of edges in and out, and this will be the number of generators at each vertex. Additionally, a key fact is that every choice of generators will create a different Cayley graph. So here's an example of the group Z2 cross Z2 and its Cayley graph. We can see here that we start with this identity element 0, 0, and we can act on it using any of these generators to get to another element in the group. So when we act on by adding 1, 0, we get across here to 1, 0. Another example is the Klein-4 group, which represents the symmetries of a rectangle, and it has a very similar looking Cayley graph. This is no coincidence, actually. We conjecture that isomorphic groups will have isomorphic Cayley graphs. So we know that the Klein-4 group and Z2 cross Z2 are group isomorphic. And clearly we see that there exists a Cayley graph of Z2 cross Z2 and a Cayley graph of the Klein-4 group, which are graph isomorphic to each other. They're here on the screen. But is this true generally? Yes, and we'll go on to prove that in a moment. But just as a sketch, we know that our Cayley graphs are dependent on the choice of generators, and that group isomorphisms map generators in one group to generators in another. So if we choose our corresponding generators and we generate our graphs using them, we should have this bijection. Let's look at that in more depth. Here we can see two groups, S3 and D3, which respectively are the permutations of three elements and the symmetries of a triangle. We can see that these two groups are isomorphic and they have the bijection as shown by the map on the left. And we can look at their Cayley graphs, given a choice of generators, on the right. And we can see that the vertices are in direct bijection as given by the map, and that everywhere we have an edge in one graph, we have the same edge in the other graph. So those edge sets are also in bijection, and that means that our graphs are graph isomorphic. Another example of that is here are two different graphs using different generators of Z6, and these are clearly not graph isomorphic, but we know that the groups are. Let's look at a proof of the conjecture. Theorem 1. Let G and H be finite groups with S a generating set of G. If G is isomorphic to H, then there exists a generating set T of H, such that the Cayley graph of G and the Cayley graph of H are isomorphic. And our proof is exactly as we've described before. Clearly, we have a bijection between the vertices given by the bijection between elements, and we can create our bijection between the edge sets using this key fact about generators being isomorphic to each other. Now, let's apply the theorem. So here we have that the rotations on a square are isomorphic to the cyclic group Z4. And here is our bijection chart, which takes 0 to E, 1 to R. Let's see if we can build an isomorphic Cayley graph using this. So here are our vertices, and we know that our vertices are in direct bijection, so 0 goes to E, 1 to R, 2 to R squared, and 3 to R cubed. So we want to build edges between these vertices which match. So here, if we use the generator 1 and the generator R, we get the same edge. Let's continue building out using that generator. And we'll see when we add 1 to 1, we get 2. When we multiply by R, we get R squared. We can complete the square, and we see that these are graph isomorphic, so our theorem has worked. Finally, some implications. Having this isomorphism bridge between graphs and groups when we study Cayley graphs can improve our understanding of both objects. And then, additionally, when we understand either graphs or groups, we can infer some useful properties about the other. This also generalizes to other areas where groups or graphs are of interest. Finally, some references. Thank you.